Hello friends, in this lecture I am going to tell you about asynchronous decade counter. As you all know, asynchronous counters are also known as the ripple counters, and decade, as its name indicates, decade means 10. So basically it is going to count 10 states. That's why it is also known as modulus 10 counter. So it can come by any of the name, like you can design the ripple counter, mod 10 ripple counter, or it can come like asynchronous decade counter. So you have to remember all the names of the asynchronous counters. Okay, now the thing is, it will count the 10 states. So the next thing is, we will decide how many flip-flops we are going to use. So if we use 3 flip-flops, that means it is going to count how many states? 8. 2 raised to the power 3, as we did in the previous counter slides. 2 raised to the power 3 equals to 8. That means if we are using the 3 flip-flops, it is going to count 8 states, 0 to 7. But we need how many states? We need 10 states. That means 0 to 9. So after 3, what comes? 4. So basically we have to see 2 raised to the power 4 equals to 16. So if we are using 4 flip-flops, it is going to count 16 states. So we will pick this one and we will use 4 flip-flops. As I have written here, to design this counter, we have to use 4 flip-flops. 2 raised to the power 4 equals to 16, because if we use 3 flip-flops, it will count till 0 to 7. So if there are 16 states, it will count to 10 and then it will move again to 0. This is called a truncated sequence. Now I will explain what is this truncated sequence. Like if we are using 4 flip-flops, that means it will count to 16 states. So I have written here all the 16 states. You all know if there are 4 input variable, you can do the 16 states. So these are all 16 states. So if you can see 0 to 9. So we need to design a counter which can count 0 till 9, which will not count 10 to 15. So this is the truncated sequence. That means it will not count this states, it will just count 0 to 9. Okay. So I have explained the truncated sequence. Counters can be designed to have a number of states in their sequence that is less than the maximum of 2 raised to the power 9. That means 9 is less than 2 raised to the power n combination. What is 2 raised to the power n combination? It is 16. It is 16. But we have to count till 9. So this type of sequence is called truncated sequence. So we can design any counter like mod 10, mod 6, mod 7, mod 8, mod 11, mod 12, mod 14. Any of the counters we can design with this simplified diagram, as I have explained in the next slide. Okay, so this is the state diagram. As you can see, I have done here 10 states: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then after 1001, it will go again count 0000. It is not going to count 1010. See, 1001 and then again it will count 0000. So this is my 0 to 9. That means mod 10 counter. So I'll explain you in the next slide how it is going to work. So I have explained here. Look here, I have used 4 flip-flops. 1, 2, 3, 4. So the thing is, in the previous counter, asynchronous counter, we have done asynchronous 2-bit counter. 3-bit and 4-bit was in the assignment. Okay, we have used the JK flip-flops. We can use the JK flip-flop as well here, but as we have done in the flip-flop slides, JK is similar to the T flip-flop. In T flip-flop, it is basically logic 1. So if we short J and K inputs, we get the T flip-flop. So I have used here T flip-flop, not the JK flip-flop, but if you want to use, you can use the JK flip-flop as well. Okay, so I have used here, because we have to use 4 counters. So it is flip-flop 0, flip-flop 1, flip-flop 2, flip-flop 3. So 4 flip-flops. Okay, thing is T0, T1, T2, T3, and in corresponding to T0 it is Q0, Q0 bar, Q1, Q1 bar, Q2, Q2 bar, Q3, Q3 bar. Okay, so and next is the clock. Clock is the negative edge. I told you in counters design we have to use the negative edge trigger so that the propagation delay is not much higher. So it is a negative edge clock pulse. So it is the first clock pulse, and in the second clock pulse the output of the first flip-flop is fed to the second clock pulse of the flip-flop, and this is the Q1 which is fed to here, and this is Q2 which is fed to the clock pulse. Okay, so this is the clock pulse. All the outputs, all the inputs are connected to the logic 1, as I have showed. T3, T2, T1 and T0 all are connected to logic 1. Now in this flip-flop I have used two things, PR and CLR. PR is preset and CLR is clear. Basically preset and clear are used in all of the flip-flops, but when we are designing 2-bit, 3-bit, 4-bit, where there is no truncated sequence, it is always 1. Okay, so there is no need to show here, but in the truncated sequence you have to show the preset and the clear. I will explain you what is preset and clear. This is preset. I have connected all the preset of the flip-flop. As you can see, I have connected to logic 1. That means if we are applying 1 here, that means 1 is going here, and that is a nibble. So basically we are applying 0. So there is no meaning of preset. If it is 0, that means it is not going to affect this flip-flop. Okay, clear also, if we are giving here 1 and it is going here 0, so there is no effect on this flip-flop for clear. So in all of the counters like 2-bit, 3-bit, 4-bit, preset and clear are 1. So I have written here preset and clear is 1 for normal operation. That's why we have not shown the preset and clear in those counters. But if you want to show preset and clear in those counters as well, you can show. Okay, now I have just made this flip-flop diagram so that you can understand what you need to do, what you need to draw the basic circuit. So the basic circuit is T0, T1, T2, T3. You have to show all the inputs, you have to show the preset, you have to show the clear, you have to show the clock pulse, the output of this is connected to this clock pulse. You have to show everything like this. Okay, now we have to show how this counter is going to count the 10 states. So this is basically the full circuit diagram, the full design of the counter which will count the 10 states. Now for this you have to understand this logic which I have explained you here. See, remember AND gate. What is the AND gate? AND gate, you know the truth table of the AND gate. If all the inputs are 1, it is going to give me 1. Okay, if any of the input is 0, it will give me 0. Okay, so all the inputs are 1, it will give you 1 here, and if we give the NOT gate here, that means it is giving you 0. Okay, so basically this is the NAND gate. If all the inputs are 1, the output is 0. So this is my NAND gate. So now as you can see here, for counting 10th state, 10, what is 10? 10 is 1 0 1 0. This is my 10 number. So Q3 is 1, Q2 is 0, Q1 is 1 and Q0 is 0. Okay, so I have to apply here all ones. So Q3 is 1, that means I will apply Q3 is 1 here. Now Q2 is 0. So see, if I will apply Q2 here, the output will be 0. We don't want 0 output. We want 1 output. So I will apply here Q2 bar. So what will be Q2 bar? Obviously Q2 is 0. So Q2 bar will be 1. So Q2 bar will be 1. This 1 will go here. Now next is Q1 is 1. So this Q1 is 1, which is going here, and then Q0. Q0 is 0 here, but we have to apply Q0 bar to make it 1. So what is Q0 bar? It is 1. So Q0 bar is 1. So basically I have to apply Q3, Q2 bar, Q1 and Q0 bar, all ones here, okay, to get the output 1, and then I will connect it to the NOT gate and I will get the 0 here. I will tell you the significance of 0, why we need 0 here. Okay, so we will use the NAND gate. So I have just replaced this circuit with a NAND gate here. This is my NAND gate, and this is Q3, this is Q2 bar, this is Q1 and this is Q0 bar, and it is giving me output 0, and this 0 I will feed to the clear. I will feed to the clear here. Now why I have feed this 0 to the clear? As I have told you, preset and clear, if it is 1, then it is the normal operation. But if clear is 0, that means now the clear will work. Why it will work? Because if I am applying 0, that means clear input is 1 here. That means clear input will work. Now I have written here 10th state. Why 10th state? Because we have to design mod 10 counter. That means that means the counter is not going to count this 10th state. It will just count to 9th state, and when it will come to 10th state, it will go to 0. That means this clear operation will do all 0, 0, 0, 0, 0. You understand this? So basically the counter will reset to 0, 0, 0, 0, and then again the counter will going to start from 1. Okay, so if we have to design mod 6 counter, so we have to do here 6th state, then after when the counter will come to count 6th state, it will not count 6th state, it will go to 0, 0, 0, 0. You understand this? So for this, what I have done, I have just connect this NAND gate. I've just connect this NAND gate to the clear, and I have shown here in this one. So when in exams you have to show this counter diagram, you need not to show this diagram. This is just for how you understand this. I have shown this. You have to just show this diagram. It is just the same as this. As you can see here, all the inputs I have shown, all the outputs I have shown, the clock pulse I have shown, logic 1 I have shown, this is the preset I have shown, the logic 1, but the clear, this clear, I have connect to the NAND gate. As you have seen, the first input is Q3, so I have connected Q3 here, right? Second input is Q2 bar, so I have connected Q2 bar from, this is my second input. Third input is Q1, so I have connected Q1 to the third input, and the fourth input is Q0 bar, so this is my Q0 bar. I have connected the Q0 bar here, and this is my NAND gate. It is giving me 0 here, and this 0 is going to all clear, right? Basically, if this is a circuit when it is going to count the 10th state, so it will go 0, then it will come in the active mode and it will reset to all 0. Otherwise it is logic 1. You understand this? So there is no need to make this diagram, just to show this diagram, to show the working of the mod 10 counter. As you can see here, I have made the NAND gate here, but so you can make the NAND gate here, you can make the NAND gate here, where you can see you can make all the connections easily. You understand this? So this is the working of the asynchronous mod 10 counter. So your assignment is you have to design mod 6 and mod 12 counter. So to design mod 6 counter, what you will do? What is 6? 6 is 0, 1, 1, 0. So basically you have to apply all ones. You understand? So whatever is 1 you have to apply like this, but whatever is 0 you have to apply the bar of it, and you have to replace this with that circuit. Okay, so that will be your mod 6 counter. Okay, so next slide is the waveforms, the timing diagram of decade counter. So this timing diagram is just as the same as we did in the asynchronous 2-bit counter, 3-bit counter and 4-bit counter. Okay, so because we have used 4 flip-flops, so it is Q0, Q1, Q2 and Q3. And the clock pulse, it has to count 10 because it is a mod 10 counter. So it is clock pulse 1, clock pulse 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this is the clock pulse, all the clock pulse. Now Q0, I told you this is the first flip-flop, so it will change its state when there is a negative edge, because we have applied the negative edge flip-flop. So it will change its position when there is a negative edge. So there is a negative edge here, so it will change its state 0 to 1 at this negative edge. Okay. Now next negative edge is here. So it will change its state from 1 to 0 here. Next negative edge is here. So it will do the transition here. Next negative edge is here, so it will do the transition here and so on. So this is my Q0. Now next is Q1. So Q1 is basically Q0 is connected to the negative edge of the Q1, negative edge clock of the Q1. So we will not see this clock pulse, we will see the clock pulse of Q0. So it will change its state when there is a negative edge. So there is a negative edge here, so it is changing its state when there is a negative state 0 to 1 at the first negative edge, and then after this there is a negative edge here. You understand this? So it will change its position when there is a next negative edge. So it changes its position 1 to 0 here. So sorry, it is basically 0. I have written it wrong. It is 0 here. Okay. So this is 0 and it will go so on. Now next is Q2. So Q2, basically the output of Q1 is connected to the negative edge of the Q2. So Q2, it will see the clock pulse of the Q1. So when there is a first negative edge, this is the first negative edge, so it will change its position like here. It's 0, 0, 0 and now it will go from 0 to 1 at this negative edge. And then there is a next negative edge here. It will change its position here and then so on. Next, last is Q3. So at the first negative edge, this is my first negative edge. So it is all 0 and it will change its position here and then all 1. So this is basically the clock pulse, the timing diagram of decade counter. And then you can cross verify here what the states it is counting. You can see here 0, 0, 0, 0. So it is 0, 0, 0, 0. It is 0 state. Then it is 0, 0, 0, 1. Okay. Then it is 0, 0, 1, 0. Then it is 0, 0, 1, 1. Then it is 0, 1, 0, 0. It's not 1. It is 0 here. I have written by mistake. It is 0, 1, 0, 1. 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1 and last is 0, 0, 0, 0. So basically it is counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and after 9 it is counting 0. It is reset to 0 and then again the cycle continues. You understand? So this is basically the timing diagram of decade counter. So you can design any counter like mod 6, mod 7, mod 5, mod 4, mod 3, mod 12, mod 14, any counter with this universal circuit. Okay. Now coming to the next slide. This is your assignment number 3. Design a mod 6 asynchronous counter. Please explain with the help of state diagram, timing diagram and the flip-flop design of the counter. So you have to design mod 6. That means it will count till 0 to 5. You understand this? 0 to 5, and when it comes to mod 6, it must clear all the states and it must be 0, 0, 0, 0. So it is just exactly the same as the mod 10 counter, but it will count till 0 to 5. And next you have to design a mod 12 ripple counter. See, I have written here ripple. Ripple means asynchronous counter. So you have to design the mod 12 counter. You have to show with the state diagram, timing diagram and flip-flop design of the counter. So whatever we have done in the previous 3 slides, you have to show everything in designing of mod 6 and mod 12 counter. Okay. So thank you so much.